Hey everyone, welcome back. Today we're doing a deep dive into something pretty mind-blowing in the world of AI and healthcare. We're looking at a brand new research paper fresh off the archive preprint server. And let me tell you, the findings are, um, well, let's just say they challenge some of the assumptions we might have about large language models. So, can AI predict the future of medical patients? More specifically, can LLMs do it better than the methods we've been using? That's the big question this research tackles. And the implications are huge, not just for the world of AI, but for actual patient outcomes.
Absolutely, and the researchers didn't mess around. They put these LLMs to the test on three common clinical prediction tasks: predicting a patient's length of stay in the hospital, their likelihood of mortality, and chances of readmission.
Right, so really getting down to the nitty-gritty of what matters in a clinical setting. And they use two massive real-world patient databases,
Yeah.
MEM3 and MEMI4.
Yeah, these are like the gold standard for this type of research,
Yeah.
providing a ton of information so researchers can really see how these models perform in a setting that's as close to the real world as you can get.
Exactly. Okay, so here's where it gets really interesting. They didn't just test one or two LLMs. They threw a whole arsenal at these tasks. We're talking 14 general-purpose LLMs and 8 that were specifically trained on medical data.
Oh yeah, some serious heavy hitters in the LLM world.
Parameter scales up to 70 billion. I mean, that's mind-boggling. They even tried different prompting engineering techniques, too, like chain of thought prompting and self-reflection prompting.
Really trying to see if they could push these LLMs to their absolute limit.
So drumroll, please. What did they find? Well, get ready to have your assumptions challenged a bit. Remember all the buzz about LLMs acing medical exams? Turns out when it comes to these specific clinical prediction tasks, the old guard traditional machine learning models like XGBoost, SVMs, RNNs, and even plain old transformers actually outperform the LLMs.
I know, right? Kind of a head scratcher. You'd think with all the hype about LLMs, they'd be blowing these traditional models out of the water. But nope, the results are in. And in many cases, the differences in scores were significant.
It's almost like, I don't know, like having a supercomputer try to solve a simple math problem.
Yeah.
Sometimes the simpler tools are just better suited for the job.
Yeah, and this study really shows how important it is to be careful when we're thinking about using LLMs for real-world problems, especially in something as important as healthcare. We can't just assume bigger and fancier is always better.
So, big takeaway here for all the AI researchers and engineers listening. We need to be cautious about just assuming LLMs are going to revolutionize every aspect of healthcare.
Definitely. This research is like a call to action to really dig into why these LLMs aren't performing as we might expect, and to look at other ways to approach these problems. Clearly, something's not quite adding up between what they can theoretically do and how they're actually performing on these specific tasks.
So, if LLMs aren't like this magic solution for clinical prediction, what's the deal?
It's a good question. What's really interesting is that even though LLMs are amazing at stuff like, medical knowledge recall, they seem to have trouble with that complex reasoning you need for predicting things in the real world of healthcare. It's kind of like knowing every medical textbook doesn't make you a great doctor automatically. You also need that real world experience and the ability to synthesize info from all sorts of sources.
Makes sense. So, did fine-tuning the LLMs on the actual clinical data make a difference?
Yeah, sometimes it did actually. They used a technique called LoRa. You can see the results in figure 4 of the paper, but it wasn't like this magic fix or anything.
Okay, so which prediction tasks saw the biggest improvement from that fine-tuning?
It worked better for length of stay and mortality prediction.
Hmm.
Compared to readmission prediction, that one was tougher. It's interesting to think about why that might be. Maybe predicting readmission needs a deeper understanding of patient behavior, social stuff, things that might not be in that structured data so much.
Right. Yeah, that's a great point. So even with fine-tuning, we might be hitting a ceiling with how much we can improve these LLMs for some of these tasks.
Exactly. And it makes you wonder, what kind of models are best suited for these tasks? This paper doesn't have all the answers, but it definitely opens up a whole new area for AI folks working in healthcare to explore.
Totally. So back to those traditional models for a sec. We talked about how they did better than the LLMs, but
Yeah.
can we dig a little deeper into what makes them tick? For example, XGBoost. What was it about that model that made it so effective?
Okay, so XGBoost, or extreme gradient boosting, it's a decision tree-based model that's become super popular in machine learning, especially for working with structured data.
Decision trees. Maybe just a quick explanation for those who aren't familiar.
Sure, imagine like a flowchart, where each branch is a decision based on some feature in the data. XGBoost combines a bunch of these decision trees to make a prediction, and it's known for being really good at handling tabular data, the kind we see a lot in electronic health records, patient demographics, lab results, medication lists, that kind of info.
So XGBoost is basically looking for patterns and connections within that structured data
Yeah.
to try and predict things like length of stay or mortality risk.
Exactly. And that kind of data is often key for making accurate predictions in healthcare.
Gotcha. That makes sense. So if XGBoost is so good at that structured data, does that mean LLMs are just bad at it?
It's not that they're bad at it, but they might not be the perfect tool for this job.
Hmm.
Remember, LLMs are trained on mountains of text data. So they're amazing at understanding language, generating text that sounds human, even doing things like summarizing medical research or answering clinical questions. But when it comes to getting insights from that structured data, models like XGBoost, which are designed specifically for that, often have an edge.
So it's like using a scalpel versus a hammer.
Exactly. You need the right tool for the job.
That's a really helpful way to think about it. Okay, so what about those other traditional models that also did well? SVMs, RNNs, and transformers. Can you give us the quick rundown on those?
Sure thing. Support vector machines, or SVMs, are really good at classifying data. They find the best boundary to separate different groups of data points. For example, you could use an SVM to put patients into different risk categories, like high risk of readmission or low risk of mortality, based on their clinical
Yeah,
features.
so basically drawing lines in the data.
Yeah. Then we have RNNs, or recurrent neural networks. They're designed for sequential data, like stuff that changes over time.
So they could analyze patterns in a patient's vital signs over time, or their medication history.
Exactly, looking for trends that might be important.
And lastly, the transformers. But wait, didn't we say those actually outperform the LLMs in this study? I thought transformers were like the core of LLMs.
You're right, it can be confusing because the term transformer gets used a lot, but they're a really flexible architecture. They can be adapted for all sorts of tasks, even ones that don't have anything to do with language.
So in this case, the transformers that were tested were probably set up to handle that tabular clinical data we were talking about before.
Right, without all the fancy language stuff.
Gotcha. So we're seeing a theme here. Even though LLMs are super impressive, we can't just assume they're the best tool for every AI job in healthcare.
Absolutely.
Now, what about the reasons why LLMs might not be performing as well as we expect in this area? The researchers pointed to a few possible explanations. What were their thoughts?
One of the biggest things they talked about was data, or the lack of it. Specifically, the lack of realistic and relevant data for training and fine-tuning these LLMs. Patient information is super sensitive, so there are all these rules and ethical considerations about how you can use it.
Right, so even these huge data sets like MIS might not be enough to capture all the complexity of real patient data.
Yeah, exactly. The researchers suggest that this lack of truly representative data could be a big reason why LLMs aren't performing as well. It's like they're trying to learn from a textbook that's missing pages, so it's harder for them to apply their knowledge to the real world.
That makes sense. So what are some potential solutions to this data problem? The researchers mentioned things like digital twins and data synthesis techniques. Could those be the key to unlocking the full power of LLMs in healthcare?
Those are really interesting ideas. Definitely worth exploring. Digital twins are kind of like, well, imagine creating a virtual version of a patient. That has all the same complexities as a real patient, but without any actual personal information.
So you're creating a synthetic data set that reflects the real world, but protects patient privacy.
Exactly. And that could be huge EE for training LLMs. We could expose them to way more scenarios and patient characteristics without any ethical concerns.
Wow, that sounds incredibly futuristic. It's like building a virtual hospital to train our AI doctors.
And then there are data synthesis techniques, too, which use algorithms to create realistic medical data that could help fill in the gaps in our existing data sets, or even create whole new ones.
So it's not just about having more data, it's about having better data.
Exactly. Data that's diverse, representative, and captures what real clinical practice is like.
Makes sense. This all sounds really promising, but I imagine there are some big hurdles to overcome.
Absolutely. It's not easy. It takes a lot of collaboration. Clinicians, data scientists, ethicists, policymakers all need to work together to figure out how to collect, share, and use data responsibly and ethically in healthcare, always keeping patient privacy and data security top of mind.
Absolutely. Well, it seems like there's a lot of work ahead, but the potential benefits for patients are enormous.
I agree. If we can get this right, it could really revolutionize healthcare.
Imagine a future where LLMs can seamlessly work alongside doctors, providing insights, helping make better decisions and improving patient outcomes.
It's definitely a future worth working towards. And this research, even though it shows some of the limitations of LLMs right now, it also gives us a path forward for innovation.
Well, I think that about wraps it up for this deep dive. We've explored the potential of LLMs for clinical prediction. We've looked at the strengths and weaknesses of different AI models. And we've even touched on some of the ethical aspects of using AI in healthcare. It's been quite a journey.
It has really interesting stuff.
Any final thoughts for our listeners before we sign off?
I think the biggest takeaway is that AI in healthcare is still very young. We're just starting to understand what's possible. There will be challenges along the way, but the potential is huge. So to all the AI researchers and engineers out there, keep pushing boundaries, keep collaborating, and never stop learning. The future of healthcare depends on it.
Couldn't have said it better myself. And to our listeners, thank you so much for joining us on this deep dive. We hope you found it informative and thought-provoking. Until next time, keep learning, keep questioning, and keep exploring the amazing world of AI.